In 1946, the world's most advanced computer needed a room the size of a house, 150,000 watts of power, and an army of engineers just to keep it running for a few hours at a time. Within a single lifetime, that impossibly bulky marvel became obsolete, replaced by invisible armies of transistors billions of times smaller and more reliable. But what forced those colossi into extinction? And how did we shrink the power of a building into the palm of your hand? The answer begins with a problem so gigantic, it nearly brought early computing to its knees. ENIAC, the world's first general-purpose electronic computer, was less a machine and more a physical presence. It filled a space of 1,800 square feet, an area larger than most houses, and stood over 2 meters tall. Inside its metal frames, 17,468 vacuum tubes glowed and hummed, each one the size of a small light bulb. Together, they pushed ENIAC's weight to 30 tons. To keep the circuits alive, the system demanded 150,000 watts of electricity, enough to power a neighborhood of 150 homes. Air conditioning units ran constantly, fighting the relentless heat pouring off the tubes. ENIAC's panels stretched wall to wall, lined with thousands of resistors, relays, and capacitors. The sheer massive bulk and appetite for energy turned every calculation into an industrial event, where computation was measured not just in speed, but in square footage and kilowatts. Heat poured off every vacuum tube, each one running so hot that touching the glass could burn skin. Inside ENIAC's metal frames, temperatures surged close to 200 degrees Celsius. Failures were constant. On average, a tube would burn out every day or two, but power cycling or sudden surges could take one out in minutes. The maintenance burden fell on teams who patrolled the rows, tube testers in hand. Gene Bartik, one of the original programmers, recalled tracing faults through a maze of wires, swapping hot tubes while the machine idled. Every breakdown stopped calculations cold, sometimes for hours. Even when ENIAC ran, the signals traveling through long wires lost strength, slowing down the very math it was built to accelerate. The physical limits of heat, fragility, and distance made it clear. A new kind of switch was desperately needed. On December 16, 1947, inside a Bell Labs laboratory, John Bardeen and Walter Brattain pressed two gold contacts just 0.05 millimeters apart onto a tiny germanium crystal. The result was the world's first working transistor, an invention smaller than a fingernail, yet powerful enough to change the future of electronics. William Shockley, their colleague, soon joined the effort, and together the trio would earn the Nobel Prize in Physics less than a decade later. Unlike vacuum tubes, this new device ran cool, needed no fragile filaments, and drew only milliwatts of power. Where a single tube was the size of a light bulb, a transistor could hide behind a postage stamp. Reliability surged. Transistors could run for years without failure, compared to the daily breakdowns of tubes. By 1954, Texas Instruments produced the first commercial silicon transistor, priced at $2.50 each. Suddenly, the barriers of heat, bulk, and fragility began to fall away. In September 1958, Jack Kilby sat alone in a quiet Texas Instruments lab and wired the world's first integrated circuit onto a sliver of germanium. That tiny chip held just one transistor, 3 resistors, and a single capacitor. Yet it opened the door to a new era, the era of integration. By 1961, Fairchild Semiconductor was shipping the first commercial ICs with 4 transistors, and the pace only accelerated. In 1971, Intel unveiled the 4004 microprocessor, packing 2,300 transistors onto a chip smaller than a fingernail. 7 years later, the Intel 8086 arrived with 29,000 transistors, laying the foundation for the x86 processors that power billions of computers today. Gordon Moore, co-founder of Intel, noticed a pattern. Every year or two, the number of transistors on a chip seemed to double. His observation, published in 1965, became known as Moore's Law, and it would define the next half-century of technological progress. Inside a modern chip factory, the scale of precision is almost beyond belief. Each 3-nanometer chip begins a 3-month journey, moving through 940 separate manufacturing steps, over 80 photomask layers, each costing hundreds of thousands of dollars. guide beams of extreme ultraviolet light just 13.5 nanometers wide, smaller than a virus, etching features into silicon. The air is filtered so thoroughly that fewer than 10 particles of dust can exist in a cubic foot, out of billions that would fill ordinary air. Dr. Chi-Wei Li describes the orchestration. Hundreds of robotic tools, each worth millions, work day and night in a spotless labyrinth, all to shape fins of silicon, just a few dozen atoms across. A modern transistor is built for control at the atomic level. A gate voltage, often just 0.3 of a volt above threshold, is enough to open a channel for electrons, switching billions of times every second. The gate's insulator is less than a nanometer thick, only a few atoms across, holding back current until the exact instant it's needed. Each switch happens in a trillionth of a second. That kind of speed and precision is why a 5-watt smartphone can deliver teraflops of performance, while the Cray 1 supercomputer needed 115,000 watts for just 160 megaflops. The physics of silicon switches made giants obsolete. Every tap, search, and call relies on billions of silent switches. As transistors shrink toward atomic limits, our digital future depends on how small we dare to dream. Thanks for watching.